life as a cancer runner fundraiser. We've done 10 of them over the course of 30 years. We've raised $600,000 plus for Relay and Cancer. This particular one was going to be huge, epic. One of the last ones we've run since COVID showed up shortly after. I think we did one in 2019. So the theme of this one was going to be Let's Fight Cancer. And so we decided to go with a boxing theme. Some of you might know of Black Eye Boxing in Brantford. So we approached them and they said, come on in. So they lent us a few things, some gloves, a bell. We actually went to their facility, took some pictures. So we had one student, very, very tiny one. She played the role of Relay, bigger, taller guy. He played the role of Cancer. And we took pictures of them in the ring, holding the boxing gloves up, and we made a big promotional poster, like, you know, we're gonna see the next boxing match of the year, boxing of the century. They were going face to face, holding their gloves up like this.
Oh my God, y'all are here.
So someone else who came late.
No, I didn't know they were going to show me.
Oh. Anyways, to finish the story, we decided to do this boxing theme. So, in order to pull it off, to really be a big relay, we wanted like 400 or 500 people there to attend the event, which means camping overnight in the middle of the track, walking the track, raising money for cancer. You get sponsored. Every student was required to get about $100 of sponsorship. They'd spend the night. We'd have live music. We'd have movies. We'd have fun games, sell food and hot dogs, things like this. And so for this particular one, trying to really maximize the number of students that participated, we had an assembly. And the assembly looked like this. Instead of your traditional stage over where the mass would be, we moved the stage right to center court. We put 4 posts up on the stage, and we put rope around the stage, we put mats on the stage, and we made it look like a boxing ring. We called everybody down, and everybody sat on the floor right around us, and then in the bleachers, which we brought in, it looked like we were in the middle of, Scotiabank. A little small, but you get the idea. On the floor, in the balconies. We had spotlights from the uppers showing down on the stage. We dropped the mic down from the ceiling, so we can go, everybody, welcome to the big event, and we welcome everybody in. We had people walking around with round one, right? They would kind of have a choreographed little thing. Cancer took the early lead. Bing, bing, bing. We kind of stopped it. We talk about Relay and what it would be and what was going to happen. Then we start round 2. Relay looked like a bit of a comeback, but Cancer had a big blow near the end of round 2. Again, we would talk about the importance of contributing. We've got to help Relay out. We got to save lives. There's lots of cancer survivors out there. Round 3 would come. Little Relay had a little bit of a comeback. Big uppercut. Cancer goes down to the mat. TKO, right? Just a knockout, and we wrapped up the assembly. On the way out, everybody received a newspaper. This was the headline in the news. Relay defeats Cancer in a knockout, kind of thing. And we handed all these out. It told the kids how to register, where to go, if you knew of anybody who was a cancer survivor, how to come. So we must have printed 1,200 of these and handed them out the day of the event. So I just stumbled on a box, still have about 100 left. I'm about to throw them in the recycling bin, but I threw them on your desk if you wanted to see what an assembly like that kind of looked like. Anyways, it was a pretty big day. 600,000, not too shabby. Here goes. Today is all about energy and momentum. I'll give you the run through from this morning. Take about a half hour of your time. I'll give you a half hour to ask any questions you may have. Period 1, or period 2, I should say, seems a little more engaged in it. Lots of people finishing the assignments, getting through the exam review, doing the practice tests. hopefully we're getting the same kind of buy-in here. For energy, energy is the ability to do something, ability to do something. And so, you know, move an object, light a light, whatever, you got this ability. The type of energies we've looked at that are important to us are potential energy, MGH, because we're not going to change the gravitational field anywhere. We're just lifting a box a couple feet. Kinetic energy, 1/2 mv squared. Again, so many students coming to me this morning. My number's not matching your number, Mr. Page. They're just not matching. I looked down. The first thing I could tell right away, you're not square. Square the blossom. Oh. So look for these things. If you're not getting the answers, did you miss something? Did you not square it? Next thing we kind of talked about is conservation. In grade 11, we just said the energy before is equal to the energy after. Technically, since energy is equal to mass, you've got to kind of consider this as an energy mass equivalency. But we're going to expand it a little bit. We're going to say if you do any work to an object, and therefore upset the balance of energy. Now this work can be a plus or minus work depending whether energy is being added or removed. In the case of friction, friction is tending to remove the energy, slowing things down. There could be scenarios where something would be applied, some sort of force, speeding things up, but not likely. Just take note of what side I get a lot of people write W over here and then they subtract it. No, I know it's friction, but if you subtract it here, it's actually positive over here. You just added the energy to it. So it's really important you understand what side. And again, I see lots of grade 12s making that kind of mistake. We transitioned over from potential kinetic and the conservation. We started to look at elastic energy. But first, we dealt with something called Hooke's law. Hooke's law simply says that as you apply more and more force, the object will have a stretch to it. And it's a very linear thing. So if this is your regular spring and then you stretch it, the amount of stretch is what X is all about. So we did a lab like this. We found that the slope is a nice constant slope. The slope of this is referred to as the spring constant. We gave it the letter K. You may say, well, isn't that the same as Coulomb's law? And technically, I use it in Coulomb's law, but remember, I believe the 1/4 pi K. So you've got this you could use instead of K. So a lot of physics would use the permittivity and the permeability of free space rather than this K. But 9 to the 9 is hard to pass up. It's so directly. And when we started to look at the energy underneath that graph, we found that the elastic energy was equal to 1/2 kx squared. All right? And so my first sample problem looks like this. Let's imagine we've got a cart up here, and the cart is 5 kilograms on top of a hill that is 4 meters high. It is moving at 2 meters per second before it comes down, meets this rough stuff right here where the coefficient is 0.3 before slamming into a spring whose spring constant is 900 newtons meters, and I'd like to know how much this will compress. Right. So for our equation to work, the energy before, any work done, energy after, you have to kind of really focus on what is going on before, what's going on after, and is there anything in between that would add or remove energy. So what kind of energy do I have here? Well, if you establish some sort of base height. Hey, this is our base height. Nothing goes below that. Let's just call that a zero height. This is higher. It would possess potential energy. Moving at 2 meters per second would also mean you have some kinetic energy. We'll come back to work in a second. Let's go down here. Sure, just as you hit the spring, you're going to be moving, but then you hit the spring and you start to compress the spring. As you compress the spring, it's getting smaller and smaller, slowing down the object until it's fully compressed, and it won't compress anymore because the object has come to rest. Height is 0, not moving. The only energy I have is elastic energy after. The work. Is there anything between point A and point B, pointing to the rough stuff here, that would take energy away? It is friction, a negative force times a distance. Okay? So over on the whiteboard we go. First thing is mgh. I have the potential energy. I have 1/2 mv squared. I'm going to take away friction times distance, and I get 1/2 kx squared. Is that the Here goes. I got a 5 kilograms times 9.8 at a height of 4. I got 1/2 of 5 kilogram moving 2 meters per second. I've got a frictional force that's 0.3 times the mass times g. That's the normal times that, and then I got to still multiply by a distance, which I didn't provide, so we'll just go 8 meters. It's going to slide 8 meters, and then it's going to collapse to a spring, and we're going to find how much. It's a one-step problem. It doesn't have to be too much from there. Here, this is 196. We do this 4 square half. We got 10 more joules here. Then we do this, and we realize that times that is 40. 40 times 0.3 is 12. 12 times that, let's say about 120-ish. And then we got 450 x squared. So you add the 10, but you take away 120 is 86. 450 x squared. Divide both sides by 450, square root it, and x is? 0.19 meters compression. Okay, so you've got this compression that's going on, conservation problem as we go. All right. Since we've introduced elastic energy, no surprise, the next thing I want to talk to you about is simple harmonic motion. This is when you have a spring. Let's call that the at rest. You stretch it out here, you give it elastic energy, you let go of it. It not only goes through this point, but it collapses way over here, and it oscillates between having elastic to kinetic to elastic to kinetic back to elastic energy. Actually kind of having this kind of sine curve as it goes between those energies. It's not that hard to say that the kinetic or the elastic energy will turn into kinetic energy. If I knew the spring constant, 800 newtons per meter, stretch it 0.2 meters, and the box is still 5 kilograms, let's go find out how fast it's moving. Again, I'm over here to solve. It's a conservation, no work done in between. Here goes, I've got 1/2 800 compressed 0.2 squared, 1/2 mass v squared. So 0.04, when you times that by 100, when you times it by 800, that would be 32. Half of 32 is 16 joules. That's 2.5 v squared. Divide by 2.5. 6.4. Square root is 2.53 meters per second. Another thing that comes about here is it's going to go through this. It's going to have a certain period of time to to go back and forth. To find the period of oscillation, it's 2 pi square root of mass divided by K. So K is an extremely high number, 800. It's a very stiff spring. When this hits it, it's going to back and forth, vibrate very quickly. The mass is 5, so 5 times divided by 800, square root that, multiplied by 2 pi will get you the period of time it takes to go back and forth in this motion. Okay? Will I ask anything about all the sine curves? The answer is no. But what you might want to just kind of focus on is knowing that this point right here is where the force is at its maximum. It's going to have its maximum acceleration. When the force becomes 0, it's all kinetic energy right here. You know, a little bit of the details about what's going on, but you don't have to know anything about the sine curves or anything to do with sine on this. Once we did elastic energy, we moved our attention to momentum. And momentum was a way of giving a quantity to a motion. So something's moving. What kind of quantity does it have? It does depend on how fast it's going, but it also depends on how much mass it has. I certainly would rather get hit by a hacky sack going 20 meters per second than a truck, right? So there is different quantities of this. We then talked about how do you change an object's momentum. Momentum, of course, being a vector. To change it, you would have to apply some force for some amount of time. The longer you apply the force, the more you will change an object's momentum. This is referred to as an impulse. So if you see on the test, go calculate the impulse for the first object. I'm looking for the change in its momentum. Its final minus its initial. mv prime minus mv. The final minus the initial.
So when you say final and initial, you mean the momentum just before it strikes, like a collision, and then after?
This is after the collision, before the collision. Or after the force is applied, like if you apply a force for 10 seconds, this is the final after the 10 seconds, before the 10 seconds happen, right? Before that. All right, so we have this. If you ever looked at a force time graph, probably realistically looks like a bell curve where the area underneath represents that. We're not going to get into bell curves. We're just going to say something simple. Oh, force peaks, force drops. What's the area? What's the change in momentum? What's the impulse that is going on? Another thing about momentum is it's conserved, and which makes it very, very useful in collisions. Anytime you see a collision, in Unit 3, you make sure you're thinking momentum first and foremost. And momentum being a vector can be talked about what's going on in X and the Y component. So in an X component, we might say, hey, momentum 1 and momentum 2 before, and a momentum 1 and a momentum 2 after. Right? We could do this in both X and Y. So let's do a quick sample of this. M2, V2 prime in the Y and in the X here. Okay? So we're going to take a problem that looks like this. We've got a car, and the car is 3,000 kilograms moving at 30 meters per second. It's going to collide with a 4,000 kilogram car moving at 40 meters per second. That's fairly fast. Okay? They're going to collide and stick together. They're obviously going to slide off to the side like that. Let's find out how fast they start this slide. We'll call the one cart in the vertical our Y. We'll call our one cart in the horizontal our red. If I did the red, I'd say, well, the 3,000 is moving 30 and collides with a 4,000 going how fast?
0.
0. It's not moving in the horizontal. They stick together for a total mass of 7,000 V prime. In the y, the 3,000 is moving how fast? 0 in the y direction. It collides with a 4,000 moving at 40. They stick together. How fast are they going in the y direction? This would be, something where we could go solve for Vx and Vy and find out what Vx and Vy are and put them together and realize where that slide is taking us. Whether it be collisions or explosions, they get handled in exactly the same way. Okay, we take this all into consideration. The type of collisions you can have are called elastic and inelastic. Elastic collisions are one where the kinetic energy before is equal to the kinetic energy after. In an inelastic, that is not the case. The most inelastic is one where they stick together. Okay, so if they stick together, that's not an elastic collision. If we go back to this elastic for a second, and not only is kinetic energy conserved, but momentum's conserved, we can come up with two equations, one for a final velocity object 1, one for a final object 2, and the equations look like this: m1 minus m2 all over m1 plus m2 times v1 add 2 m2 v2 all over m1 plus m2. Over here, it starts with 2 m1 v1 all over m1 plus m2, and you add m2 minus m1 times v2 all over m1 plus m2. And I told period 1, make sure your cheat sheet has these, because I think it was as early as semester 1 where I didn't have it on the cheat sheet. So here's my sample problem for this. We got the red cart, and the red cart is 5 kilograms and it's moving at 5 meters per second. It's going to collide with a blue cart, 3 kilograms, moving at 3 meters per second. This is going to be a head-on collision, folks. 5 and 3 coming at each other, and we're going to find their final velocities. Again, I'm over here on the whiteboard to solve. Momentum is vectors. If you choose to ignore the vectors, you're going to make some huge mistakes. Period 2, I changed the problem. They were doing this. You're going to do this one just to make it interesting for me, but the plus minus signs are important. So for V1 prime, it would look like this. It would be M1, 5 minus M2, 3 over M1 plus M2, 8 times the initial speed of 1, 5. We're going to go 2 times M2, which is 3, and it's moving at minus 3 all over 8. V2 prime looks like this. 2 times the first mass times the first speed over total mass, plus M2, which is the 3 minus 5, going a speed of minus 3 at a total mass of 8. Let's go and solve. This is 2 times 5 is 10, 8 over here. This is 6 times this is minus 54 eighths, which is minus 44 eighths, which is minus 5.5 meters per second. The negative means something. Over here, 5 times 5 is 25, times 2 is 50 eighths. Over here, I'm going to add a minus 2 times a minus 3, or 6 eighths. That's 56 eighths, or 7 meters per second. Okay? Those plus minuses are really important to us in terms of what will happen to these carts after the collision, assuming that it's a head-on elastic collision where they're bouncing off of each other. Meanwhile, we've also done something like this where we said that first cart, that 5 moving 5 meters per second, has a spring on it, and it's going to collide with the 3 going this way at 3. And because it's elastic, During the collision, there will be a moment when that spring is super compressed. Let's imagine that this K value is 500 newtons per meter. Let's find out how much this collision is going to collapse it. Well, that's energy. Energy is going into the spring. So I can tell you a little bit about the energy before. This card here was going 5 times 5 squared, and this cart is 3, so minus 3 squared, and that's 25, 125, 62 and a half, 62 and a half. That sound right?
Yep.
25, 125. Over here, this is 9, 9 times 3 is 27, half of 27 is 13 and a half. This is going to be 76 joules of energy. This is before they even collide. Then at some point here, when this is at its maximum compression, they'll be traveling like they're together. It's like the 5 was coming in at 5, struck a 3 going minus 3, and they're going to stick together with some v prime. 25 minus 9 is 16. And that would make my v prime 2 meters per second. That's 2 bodies, total mass of 8, moving 2 meters per second. 2 squared is 4, half of 4 is 2. This is only 16 joules of energy. Wait, I had 76 joules. I'm down to 16 joules. I lost 60 joules. Where did it go? It went into the elastic energy. So 1/2 500 is 60, 1/2 of 500, x squared is equal to 60. X squared is 120 divided by 500, okay? So that's like 1.5 divided by 5. I'm going to say 0.24, and then I would have to square root that, and I would get 0.48.
Yep. 0.49 if you round.
Let's round. 0.49 meters as the maximum compression using conservation of
Where did you
energy.
get the 54 from? Or not?
The 50? Is it not 50?
54. Should be 18.
Where are we going back to here?
Up above 54 over 8.
618. Yeah, this is wrong, right?
Yeah, it should be -1.
Minus 1. Thank you. Where did I get 54? I think I squared it. Think about it. 6 times 9, 54. I think that's what I accidentally squared something. All right, so we found the compression in this spring here. I think we kind of left off with the ballistic pendulum. So let's do one of those kind of problems to wrap it up. In a ballistic pendulum, you've got, let's say, a rope. Let's say it's 1 meter of rope, 1 kilogram box. We got a bullet, 10 grams or 0.1 kilograms. Let's say this is moving in at 100 meters per second. Okay, it's not a conservation of energy. This bullet's energy, this kinetic energy, strikes this. The energy doesn't stay the same. We lose so much heat and friction and sound. Okay, so this hitting this is not a good problem for conservation of energy. But what it is it's a good problem for conservation of momentum. There's a collision. Mass 1 hits mass 2. They stick together, and they're going some v prime. So I've got 0.01 times 100 strikes 1 doing nothing. Together, 101, and this is 1, this is nothing. So my v prime is about 0.99 meters per second, is my guess. Maybe an extra little decimal point. I know how fast this is going. Okay? If you did the energy here, kinetic energy, 1/2, 101 moving 0.99 squared. When you square this, it's almost 1. 1 squared times 1, this should be about 0.5 joules. But when you took the energy here, just as a matter of discussion, it was going 100 squared. 100 squared times this is 100. Half of 100 is 50 joules. I went from 50 joules to half a joule. That's what I'm saying, the energy is not conserved. But this half joule, as this swings through, this half joule becomes potential energy. The kinetic energy before becomes the potential energy afterwards. So this half joule is equal to 1, the mass is 1 times G times H. And so H works out to be really close to 0.505 meters, or about 5 centimeters. Remember, this was 1 meter long, or 100 centimeters. I only climbed 5 centimeters. That makes from here to here 95 centimeters. If you prefer, 1 and 0.95 meters. But you could find this angle easy enough. You've got a triangle in here where you know the hypotenuse and the adjacent. Do some coastlaw and you've got yourself an answer. Is there any questions that I can do for you? Take a look at your assignments, your test. I'm here to serve.
Like a grenade.
A grenade. Let's do a grenade one.
He said maximum pressure.
Okay. So we're going to treat a grenade problem much like we would a conservation of momentum, like a collision. All right, so here goes. I'm just going to make a pretend grenade up. Let's say it's going to blow up into 3 easy pieces. The grenade, by the way, is 1 kilogram. It's a big explosive. Piece 1 goes flying this way. It is 0.4 kilograms and goes off at 40 meters per second, but heads in a direction of east 30 north. There's another piece that flies off this way. It's a little smaller at 0.3 kilograms. And it's flying just above the west, say west 10 degrees north, but it is going at 50 meters per second. There is a third piece. You probably have already figured out its mass is 0.3. Where does it go? That's my question. So what you're going to do is you're going to say that the momentum in the x before is equal to the momentum x after, and in the y, the before is equal to the after. So in the x direction, here goes. The whole thing was 1 kilogram and it wasn't moving. Afterwards, a 0.4 goes at 40 meters per second, but coasts of 30 degrees. We add to that a 0.3 going 50, but head off at coast of, anybody want to guess? West 10 to north. 170 is perfect. The third piece is 0.3, and I have no information whatsoever. Let's just call it Vx prime. Being the only thing that we don't know, we should be able to work out my Vx prime. Let's do the y. Again, I got a grenade that wasn't moving. I got a 0.4 going 40, but sine for this one, 30 degrees. I got a 0.3 going 50, sine of 170. And I got a 0.3 doing Vy prime. You gotta go find this Vy prime, the Vx prime, and you can put it together. Does that make sense? Anything else?
There was a question where we did for one of the examples during this. There was a 8-ball question.
Yeah.
Could you please redo that?
The 8-ball?
Yeah.
Not all that different from what we're just doing, but because it's slightly different, we can do that. We've got an 8-ball here, we've got the cue ball here. The cue ball is, let's say, 0.2 kilograms. Let's say this is 0.2 kilograms. Let's say I hit it at 10 meters per second. The 8-ball goes this way afterwards. It moves at 8 meters per second at an angle of 50 degrees. What is the cue ball doing after the problem? Is this okay?
Mhm.
Alright, so I'm going to take a collision, I'm gonna think about what's going on in the X and what's going on in the Y. In the X, I have the 0.2 coming in at 10, hitting a 0.2 that's probably doing nothing, right? That's the object of the game. The cue ball afterwards, don't know, but the 8 ball afterwards is going 8 cos of 50 degrees. You realize if they're the same mass, I don't even have to worry about the mass, it's just the velocities that are really important. And I have 10 over here and then 8 cos 50 plus Vx prime. Easy enough to go find Vx prime. That's gonna be this piece of the puzzle. Okay? To get Vy prime, we just have to know that the 2 was doing nothing, hits at 0.2 that was doing nothing. Because the cue ball isn't going this way, it's all in the X direction. Afterwards, the cue ball is doing something I don't know, but the 8 ball is going at 8 meters per second, sine of 50. So again, that mass doesn't really matter. I've got 0 is equal to Vy prime, 8 sine 50. You go find Vy prime, a squared, b squared, c squared, and find the final velocity.
Okay.
Next.
Could you quickly explain why we do sine in the y and cos in the x?
Okay. If we're in quadrant 1, if you're in quadrant 1, I think it becomes fairly easy. Let's say this is 60 degrees. This is the opposite side, right? Opposite side, hypotenuse. Now the hypotenuse is usually what I give you. I say it's going at this speed, at this angle. So this is, I give you this. Opposite over hypotenuse is sine. So if you multiply the hypotenuse times sine of the angle, that will tell you how much this one is. And cos, of course, is the same thing to get me the adjacent. And if you go right around 360, as long as the x is always given as 360 degrees, it will always tell you cos for the x and sine for the y. No? Anybody else? We're getting close to that 30-minute mark where you can now, flex your muscle, try the practice test, try the review, do something useful with your time. Okay? If you want to, come on up, ask some questions. I gotta do attendance, because we have a number of people who aren't making it, which is surprising since some people's marks are on the line.
Not really.
We